Welcome everybody to week 10, day 3. Today is mostly going to be lab time, but we are going to continue our exploration of pointers and the difference between a pointer array, a 2D array, and a vector. And this is relevant because your homework assignment returns a 1D vector that is holding 2D data. And I can show you 3 different ways that I could think of doing that. So if I wanted to hold a 2D array with like elevation data in it, the elevation data is ints, I could do it 3 different ways. I could give you a 10 by 10 vector like this that is a vector of ints. Each row is size big. Each the whole thing is size columns tall, and you can just sit there and adjust the size to whatever you want. It's now a 10 by 10 grid filled with numbers. And I can set row 5, column 3 to be -1, like this. Or I can set it like this. Vectors work with both square brackets and .at. My recommendation for new students is to always use .at. So this means .at row 5, .at column 3. It's always row first, then column, which is Y, then X. That's something that like gets a lot of people, myself included. We always want to do X first, then Y, but X is the column and Y is the row. And so theoretically, if you're consistent in it, then you won't notice any difference as long as it's square. But really, this is the number of rows you have. This is the number of rows you have here. And this is how many columns you have here. Okay. And you can access row 5, column 3, like this. One of these 2 ways. This is the safer way. This is the more dangerous way. Now, if you don't want to use a vector, and why wouldn't you, right? You should, honestly, maybe. I don't know. Then you can make a 2-dimensional array like this, int array 1, because I'm about to do another array down here. And it is a 10 by 10 array, which is all initialized to 0. Okay. And I can set row 5, column 3 using the square bracket operators like this, and this will set row 5, column 3 to be -1. Or I could do it using a 1D array, and this is how your homework assignment starts. And there's actually really good reasons to use 1D arrays when you're like, well, it should be a 2D array, right? It's a 2-dimensional map of data. There's actually really good reasons to use 1D arrays, and my master's degree was in computer science, but my specialization was in high performance computing, and 1-dimensional arrays are kind of used everywhere. And what we do is we use the powers of algebra to figure out, based on this row and this column, where in the 1D array the data is located, and then we index into it that way. So I'm going to go through the math on that in just a second, but you can see here I'm making a array that is the same number of elements, right? Like this one is 10 by 10. So 10 by 10 is 100 elements, right? And this one is, well, it's 100 by 1. It's a 1-dimensional array. And it's got 100 elements in it. So you see, they actually take the same amount of size. Like one is a 10 by 10. Another's 100 by 1. They're both exactly the same amount of RAM. And in actuality, they're pretty much the same thing. You just have to do a little bit of algebra to figure out where in the 1D array you are. And this is row 5, column 3. And this algebra looks complicated, so I'm going to explain it. I'm going to sort of build an intuition in your head of how, this thing's working, and then I'll come back here and explain it some more. So let me switch to OneNote, and let me draw this out for you. So if we've got a, switch over here, and we can do a 2D array. So if we've got a 2D array, this is a 4 by 4. So size is 4 here. This one here is row 0, column 0. Okay. So if we were to draw a 1D array that had size 16, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, something like that, then this spot here, like if we put a 42 into here, would be the same thing as putting a 42 into here. Row 0, column 0 is the same thing as index 0 in a 1D array. And this one is the same as index 1, this one's the same as index 2, this one's the same as index 3. Now we've hit the end of the row. What index should this person be in the 1D array down here? What do you guys think? These are just the indices, really. Yeah, this should be 4, right? And then we move 1 to the right, and the index goes up by 1. So 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. And then the next row down is going to be which one? What's the index going to be for this guy? 8. And if I were to go down to this one, which one is it? What's the index of this person? Follow the algebraic pattern. 12. Very good. Because every time you go down a row, it's like you've moved right 1, 2, 3, 4. Right? Does that make sense? So if you're here at 5 and you go down 1, that's like adding 4 to the number, right? Because we have a size of 4. Does that make sense? So yeah, in the Bridges Mountains code, you'll see them like add size to the index, and you're like, what the heck is that all about? You know what I mean? So like, if you want to travel east, that's the same as doing what? Adding what to our index. So if we're at index 5 right now, and I want to get the location of the spot to the east, what do I add to it? 1. Yeah, very good. So plus 1 is the same as like go east, young man. Let's go west. Okay. And then if you want to go down a row, that's like adding what? So going east is like adding 1. Going down is like adding 4. Good. And so going southeast is like adding what? If you want to go southeast, it's like going south and east. So it's plus 5, right? So for whatever your index is in this 1D array here, so if you're currently looking at the elevation here, which might be, I don't know, like 1,000 or something, it's 1,000 feet up. If you want to get the elevation of the person to the southeast of you, you check the value at index 6, 7. Make this maybe a little bit more clear. I'm going to draw the indices above the thing. So index 1, index 2, index 3, index 4, index 5, index 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 is the last one. Okay, so if I am currently in Colorado somewhere for your homework assignment, you're going to have a whole bunch of elevation data, and it's all held in a 1D array like this. If you want to get the elevation of the person east of you, which index am I going to grab? I'm currently here. I'm currently at index 5. If I want to get the elevation of the person east of me, what number do I look at? 6. Very good. So maybe that one's elevation is 1,200. And then if I want to grab the elevation of the person northeast, and by person I mean like location, if I want to grab the index of the person northeast of me, then I subtract 4, right? Because going up is like -4, and then I add 1 to go east. So -4 plus 1 is what? If I want to travel northeast, that's like subtracting 3, right? Size plus 1. And so the elevation there might be like 500. Right, elevation 2, sorry. Index 2, rather. So that one might be 500. This one might be 1,200. And this one might be like 1,600. And so this one's elevation is 5 to the right, 1,600. And so for your programming assignment, the hardest thing in this thing is saying, all right, I'm currently at row 1, column 1, row 1, column 1. So that's index 5. And it's index 5 because I've gone down 1 row, right? Because I'm on row 1. I've gone east 1 column because I'm on column 1. And so it's 4 times 1 plus 1. Does that make sense? So it's algebra. And the index into the 1D array is the row you're on times the size plus the column. This equation you will see all throughout computer science. And it makes sense if you just like stop and think about it for a second. Like these things are numbered like you're reading a book. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? And so every time you go down, you're adding the width to it, right? Because every row has 4 people in it. So if you go down a row, you've just skipped over 4 people. Does that make sense? So every time you go down a row, you have to skip over however many people are in a row, right? Makes sense? So if you head south from 11, you're going to be at 15 because there's 4 people in a row. 11, 12, 13, 14. So you skip over 4 people and you're now at 15. If you want to head west, that's like subtracting 1. If you head north, it's like minusing 4. Okay. What is the size? This is a 4 by 4 map. So my map here is 4 by 4. Size is the dimension, the width, and the height, because we're using a square map right now. Does that make sense, Kara? Do you understand what size means? Okay. And you will see this equation in the sample code. You're probably like, the hell is that? You know? So let's hop back over here. And you can see I've got the equation in here. But let's do it by hand. So I've got a 10 by 10 map filled with data. It's not, but it's filled with data. And it's filled with zeros, actually. Okay. And let's say I want to set row 5, column 3 to be -1. What index is that? So I've got a 10 by 10 grid. Got a 10 by 10 grid. I don't know if I want to draw this out, but I've got a 10 by 10 grid. Whatever. Got a 10 by 10 grid. And I want to go down to row 5 and column 3. What is that index? Right? Remember, the index of the top left corner is 0. Index 1, index 2, index 3, index 4, 5, 6, 7, 8, 9, and then row 1, column 0 is 10, 11, 12. So what is that one? We've gone down 5 rows. Every time you go down a row, it's like adding 10, because we have a 10 by 10 grid. And every time we go east, it's like adding 1. So if we've gone down 5 times and we've gone east 3 times, what is our index? So it's like we're accessing element 5, bracket 3. Right, that's how we did it here. But now we just need a single number to put in here. Because it's honestly, even though you're like, how is this easier? 1D arrays are actually easier to work with than 2D arrays. And I'll show you why in a second. And it just means you have to like understand the algebra behind it. Okay. So this is 53. Yeah. It is 53. Because if you were on row 0, column 0, then your index would be 0. If you were on row 1, column 0, your index would be 10. Because we have a 10 by 10 grid right now. Okay. So every time you go down a row, it's like adding 10. We've gone down 5 times. It's plus 50. We've had traveled east 3 times. So 53. Okay. So let's give you guys a couple more challenges. So yeah, we can say 53 here, and there we go. This and this are basically doing exactly the same thing. Okay, so let's try a new challenge. Let's say row 8, column 1. So what do I put in here now? What index is row 8, column 1? 81. You guys are on fire. Okay. What about row 2, column 7? Row 2, column 7. What index does that correspond to? 27. Very good. Do you guys get the math? So every time you go down a row, you skip over however many elements are in a row, and that is 10 in this case. Okay, so let's make it a little harder. Let's make it not the power of 10. Power of 10s make it too easy for you. Let's make it 100 by 100. Okay. So, same thing. Row 2, column 7. Every time we travel down, the index goes up by 100. We've traveled down twice. Every time we travel east one column, it's plus 1. Is it 207 or is it 270? Every time you travel east, the index goes up by 1. You have to travel east 100 times to go down 1. Because it's 100 by 100, right? So you have to go east, 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 and 100 easts equals 1 south. Okay. 207, very good. Yep. Every time you travel south, that's 100. Every time you travel east, that's 7. So there you go. So what is the index? What is the index of the tile, the square, northwest of us? We're at 27, right? So what is the index location in a 1D array of the person north once and west once? So to go north, we have to subtract 100, right? And this whole thing, by the way, is called learning point for today. Learning point number 1 for today. 2D to 1D array mapping. Okay. And it's just algebra. And when you do something like this, the language itself does the algebra for you. That's all it's doing. It actually is probably going to compile down to probably exactly the same code, where it's going to take 5 and multiply 5 by the size, which is 500, and add 3 to it, and be index 503. It's just doing the algebra for you. And you're like, well, why would I want to do the algebra myself? So I'll show you in a second. So if we go north, that's minus 100. If we go west, that's minus 1. So index 106. Okay? And that's how your homework is laid out. That's why it's kind of important for you to know this. If you haven't had this lecture, you're going to be very confused as to why there is 2D map data held in a 1D array. And you're like, wait, how do I get row 5, column 6 out of it? And this is the answer. So the answer for everything is always going to be your row times the size of the map plus the column. This equation right here, you will see everywhere in computer science. Okay, because 2D to 1D array mapping is very common, and there's a more complicated version for 3D to 1D, where it's the plane times the size of a plane plus the row times the size of a row plus the column, and that's the 1D array index if you're holding 3D data in a 1D array, which we do a lot. Okay, so let me tell you why this is annoying. A 2D array is annoying. Okay. Are vectors annoying? Not really, actually. If you want to refactor your code so that you don't have to deal with any of this stuff, you're more than welcome to. In fact, there are 2 paths forward for this homework assignment. Option 1 for your homework assignment is to refactor the code. So you're going to have to rip out all of the code involving 1D arrays and news and deletes and things like that, and replace them with vectors instead. So you kind of like find the place where the memory is nude, replace it with a vector, you return the vector, so the return type has to change. I'll give you an example of this later on. But basically you have to kind of like follow the path that your map data takes through the code and replace every instance of a 1D array with probably a 2D vector. And then life's easy after you've refactored it. Refactoring means changing code to be better. Okay. And it takes effort to refactor, which is why a lot of companies don't refactor their code probably as often as they should, because they're changing existing code that works already. So why bother? So a lot of old code will just kind of like sit around and stagnate. They're also afraid of breaking something, right? And then the other way of doing the homework assignment, if you don't want to refactor it, if you want to stick with the 1D array method, you can gain understanding, okay, gain enlightenment of the. This code is from SeaWorld. Okay, And C is like a more popular programming language than C++, even though C++ is arguably better in every way, shape, and form, because it can do everything C can do plus more with very few exceptions. One of which we might actually even get to today. C is still an incredibly popular language, and there's a lot of people that program C++ as if they were programming C. It's a very common programming style, and you need to become comfortable with it, right? And so you kind of come to the realization that a 1D array and a 2D array are really the same thing under the hood. You know, this here, and you know, this here is basically going to be we're basically going to be doing the same thing, you know. So it's just here the compiler does the algebra for you. Okay, now learning point number 2. 2D C-style arrays kinda really do suck. Okay, so let me show you why they kind of suck. They don't entirely suck, but they kind of do. All right, so they suck because they're hard to pass to functions. So let's say that you were going to pass a array, like a 1D array, a normal array, to a function. In C world, you do it like this. You'd say like void print array, and you're going to take in like a pointer to an array, and you're taking a size. And this is very common. In C, you pretty much always see this pattern, where you have a pointer and a size. And that tells you the beginning and the end. If you don't have that, then, oh boy. Oh boy. All right, so we've got this. I'm going to do something like this. Actually, we don't even have to pass it in because we technically have the size as a global up here. So if we wish to live dangerously, we can just use the global because all throughout our code we're using that global for the size of the array. So yeah, we can do it this way. All right, so for int I equals 0, I is less than size, I plus plus, y2, yp, right arrow twice, that is, and there. Remember, every time you copy paste, scan through everything to look for any places that needs to be changed. If you change one of those and not another, you're gonna have an infinite loop. Okay, so okay, and so we're just gonna like see out our square bracket. I is the row, j is the column, and always remember that row comes first. It's called row major ordering. Okay, we're gonna make that a learning point for today. Learning point. Number 3, row, which is to say y comes first. Okay, so it's always y then x, not x then y. And that's something that a lot of people, myself included, make a lot of mistakes on. Okay, so it's going to be the row, which is I, times the size of the array, plus j. There's our algebraic equation. Like I said, it comes up a lot. So we're going to print out row I, column j, followed by space or something. And then at the end of the row, we will see out a new line, and there we go. So we've got a function that can print array 2, and we don't even need to pass in the size, which is what I was doing before, because we got a global that tells us the size, and it's kind of not great, but it's also workable. And so here we go. So you can see that we have changed row 1, column 6 to -1. Row 1 is this one. 0, 1, 2, 3, 4, 5, 6 is set to -1. And we can do something like, what is it, a 10 by 10? So we can set like 42 to be -420. And you can see row 4, 0, 1, 2, 3, 4, column 0, 1, 2 is successfully set to -420. Okay, any questions about this? Why do we hold a 3D and a 1D? Why? Why do we hold a 3D and a 1D? Because it's annoying. I'm getting to it. So I'm showing you the 1D up here. Now let's say we're going to do the same thing, but for a 2D array, right? So the trouble with the 2D array is that the size actually has to be fixed in the function parameter. Normally, when we do something like this, we do it like this, where we pass in a pointer and a size. You can't do that with a 2D array. You can't do that with a 3D array. And that's why they suck. Okay? So, kind of suck because they can't pass in size. That's why they suck. Now, if you have something like this where the size is fixed, it's okay. But like I said, most of the time when you work with pointers, you know, like you're going to be newing memory and stuff like that. You don't know how big it's going to be. And so you can't actually have a function that takes a 2D array of arbitrary size. And that sucks. So let me show you what I mean. So let's say I wanted to make a void print array that takes an int array 10 by 10. Or I can make this like size by size. And then this is just going to be a 2D array. And we can print this one. So now we've got a print array function that works with a 2D array. Cool. All right, everything's fine. Everything's cool. All right, so we will set 9, 9 to be negative 999. And so you can see negative 99, the bottom right corner of the first array is set to negative 999. Cool, right? Everything's fine. What are you complaining about? What are you complaining about? It's all fine. Well, it's only fine because the array has a fixed size. And we know that every time we call this function, array is going to be 10 by 10. Okay? You notice here, it doesn't have a size baked into it. You could, if you wanted to, bake in a size like this. That's fine. With that. But you can do, with 1D arrays, you can have 1D arrays of different sizes. Like I said, most of the time when you do something like this in C, you're going to pass in a pointer and a size. And you can't do that with this. If you try, here, let me show you. If you try, then, like, let's say you take that out, which actually you can. Watch this. Works fine. The number inside of here is actually ignored. But this number here, yeah, it's weird, right? It needs to know how big every row is, but it actually doesn't need to know how many rows you have. It's actually completely optional for you to put in that number there. But if you were to take this number out, then it won't compile. So it's a weird bit of weirdness. There's a good reason for it, but you must put the row size, which is how many columns, in the type. Okay, so you cannot have something like this. This won't work because you do not have the size of it in there. It has to be baked into the type of the function. You can't have a variable sized 2D array passed in. That's why they kind of suck. Because usually when you have an array, you want to pass them to a function. And you kind of can't unless you know every time exactly how big your array is going to be. And if you want to change how big your array is going to be, you have to edit this and recompile your entire program to have a different sized array. Or you have a different version of the print array function for every size array that you have in your code, and that's terrible. And so what we end up doing in high performance computing is we just pass a pointer, boop. You just pass a pointer and a size to everything, and everything just operates on a 1D array as if it was a 2D array. And we do the algebra. Okay. And we'll typically pass in the width and the height to it. So if you have a rectangle, right, then it's not the same size for both. You pass in width, you pass in height, and then you do your little bit of algebra. So this is far more common, especially with a size than this. You can't do it this way. With a 2D array, the width of a row, how many columns you have, has to be fixed, baked into the type, which sucks. Okay. All right. And then, of course, the other alternative is void print vector, and vectors are wonderful. You should always use vectors. So should this be, I'm going to pass in a vector, right? But should this vector be called by reference, called by value, called by const reference? We're going to be printing the vector. Not changing it. Printing the vector. Should it be called by value, called by reference, called by const reference? Vote now. Operators are standing by. I'm going to pass in a vector events. Let's see. Close angle bracket. Yes, you guys all got it. You're all smart and brilliant individuals. Yes, it should be const reference like that. And then, because it's a vector, guess what? It comes with the size. Yeah, that's cool. We don't have all this nonsense with sizes and having to hope that that size being passed in matches the actual size. Nah, the vectors come with their own size. So we can do something like this. For every const auto referenced row. So for every row in the vector, for every const, it doesn't matter, just int x. For every int in the row, remember it's a primitive. Primitives, generally speaking, you want to use call by value with primitives. Call by const reference for a row, it's a vector. When you have a 2D vector, it's actually not a 2D vector. It's a vector of vectors. And so each entry in the vector is itself a vector. And so you have like a bunch of vectors. So this is actually a vector here. Each row is actually a vector, and then we're saying for every integer in that vector, we are going to cout it to the screen. And then at the end of the row, we'll hit return. And if we come in here, we'll do a print vector, passing in vec. What's your vector, Victor? All right, there we go. And for this one, we will set row 2, column 9 to be 290. And too large to be represented. That's fair. Okay. And then we will set, I don't know, 1, 1 to be -1. Slap an extra end line between these things here. Print array, print array. And you are also not needed. Okay. So we got our 3 different options here. Throw in a new line between each one. So you can see 1, 1 is set to -1. Row 2, column 9 was set to 290. 99 was set to -999 on that one. Row 1, column, was it 6 or so? To -1. Row 4, column 2 was set to -420. Okay. So we got 3 different options for doing the exact same code. All right. So we've got a vector that's a vector of vectors, which is a 2D vector. And you can set the row and column this way. So you're setting the value at a certain row, a certain column. You can make a 2D array like this, and then set the row and column like that. You can make a 1D array that's like a 2D array. It's a 1D array, but it pretends to be a 2D array because we know the algebra. And so by doing 2D to 1D mapping, we can treat this big 1D array as if it was 2D, two-dimensional data. Okay? And that's how your homework assignment does it. That's why I'm having this lecture right now, because it will confuse the hell out of you if you've never heard this lecture before. Okay. So so you just use this formula right there. That's the formula. Okay. I'll write this down so it'll be in your notes. This is the super formula. Okay. 2D to 1D mapping looks like this. It is going to be row times width plus column. And if you want the 3D to 1D mapping, just because, I don't know, you're looking at this in the future and you want to see how to map from a 3D array into a 1D array, which is, again, very common. They're a lot easier. 1D arrays are a lot easier to work with. They're also contiguous in memory, which is an advantage that these don't have. Vectors are not necessarily next to each other in memory, so you're actually passing a bunch of different memory addresses around. With the 1D array, you just pass a single memory address. It's actually faster. Okay, so for 3D to 1D mapping, we're going to say what plane we're on times the plane times width times height plus the row height plus the row times width plus the column. So that's the 3D equation. So every time you go down a plane would be like 10 by 10 or something like that. Every time you go down in the z direction, you've moved 100, right? If it's 10 by 10, you've gone 10, 10, 10, 10, 10 times, right? So when you go down 1 in the z direction, it's like advancing 100 through the 1D array. Does that make sense? Like conceptually? If you have a 20 by 20, like if each plane is 20 by 20, there's 400 entries on it. And so if you go down to the next plane, you've advanced 400. Cool. So, and width and height don't have to be, it doesn't have to be square, but I'm just using it to make the math easier. So if you had 20 entries per row and 20 rows, there's 400 people on a plane. So if you go down to the next plane, you've moved 400 ahead. And then every time you go down a row, you've moved 20 ahead. It's like going 20 to the right is 1 down. And then going 1 to the right is 1 down. Okay. So you don't need this for this one, but it's, like I said, this equation will crop up a lot in your computer science career. You'll probably use it next semester, and you'll use it in 26 for sure. Okay, so here are our 3 options. Which one do you guys prefer? Like, if you could just wave a magic wand and not have to refactor it yourself, which one would you prefer? Would you prefer working with 2D data using a vector of vectors, option 1, with a 2D array, option 2, or with a 1D array, option 3? What is your pick of choice? 1/3? Option 1, option 3, option 1. Yeah, I for this homework assignment, I actually implemented it both ways. And from a purely speed perspective, I think the option 3 is actually a little bit faster. But for like ease of reading, it's a lot easier to do option 1 because you can just give it a row and a column and get the elevation there. Whereas with this, there's like all this elevation, like we want to get the spot to the east and to the northeast and to the southeast, and so we have to advance width and add 1. So just depends. If you're scared of algebra, use option 1. But option 1 has the downside of like you have to refactor your code. So the code that you're given is in a C style, C++, written in a C style. And so you got to go through and refactor your code. So let me show you what that looks like. So let's say that you had code that did something like this. So refactoring is the thing. Actually, both of these options here, both option 1 and option 2, these are actually both really valuable skills to have in computer science. Unfortunately, I can only make you do one of them because you have to solve the assignment, right? So either you refactor, and that's a great skill to have. The ability to take existing code and improve it without breaking it is an incredible, very super valuable skill to have. That's one approach. Another approach you can do is to understand this 2D to 1D mapping thing and to understand the C way of doing things. And that's also really valuable because there's a lot of programs, probably more programs are still written today in C-style C++ than they are in modern C++. So these are both extremely valuable job skills and probably something you might want to just try doing the homework both ways. I did. So you got a giant group. I mean, you might as well have somebody try it both ways, right? Take both approaches, see which one works better for you. Okay, so let's say we're going to refactor code, and it's got something like this, like int pointer make array, and it is going to integer pointer r equals new int size times size. So this is going to like allocate memory to hold our map, and then we return our. Technically, we can put these on one line. We don't need them on 2 lines. It's fine. And so this is going to return an owning pointer. And this, you know, it'd be something like this. We got make array. So So something like that. Okay. So that it's going to allocate 100 integers off the heap. This one's off the stack, right? Talked about this last time. This is stack allocation. You don't need to delete anything off the stack. This is heap allocation. So what do I need to add right now to fix this? I mean, obviously can't have both. But what do I need to add? I've got a new inside of make array here. This is returning an owning pointer. This is a way that people code. Don't recommend it, but they code this way. And so it's returning a pointer that owns a chunk of memory. For every new, I need a what? Delete, very good. So after I'm done with it, I need to come in here and say delete R2. Okay. Using the array deletion. There's two different deleters, one with brackets, one without brackets, and you have to know which one to use. Which is another bit of annoyance, which is another reason why I don't like using new and delete. I like using vectors instead. Handles it for me. Okay. So this is very common code, and this is how your homework assignment looks. It calls a function, the function allocates memory, and then returns an owning pointer to it. And then it originally didn't have the delete, so I added a delete at the bottom to clean up the memory leak. So let's say this is our situation, and we've got a function that we're passing it to. Okay, we got one here. Cool. All right, and we want to refactor it. Okay, so we want to pull out this code using pointers and news and deletes and all this stuff, and we want to replace it with vectors, a 2D vector, in fact. So you take it one step at a time. Okay, so you go to the origin, you go to the source of the Nile, right? And okay, so we're living in the state of denial right now. And here is the origin of that. So what we're going to do is we're going to replace that, comment it out so you don't forget. Don't delete things and then forget what you were doing. And so I'm going to make here a vector of vectors of ints named, I'll just keep the name the same, even though it's a vector now, r, whatever. And it's of size, and each row is a vector of integers of size as well. And I'm going to return it, and now this won't compile. Why? Step 2, change the return type. You see how this works? You change it in one place, then something breaks. And so you go, oh yeah, that's a good point. I need to fix that. So this needs to be a vector of integers, because we are returning a vector of integers now. Not an array anymore, not a pointer. Pointers are arrays are pointers 99% of the time. So come down here, and now this is broken, right? Why is this broken? What's going on here? Why is it mad at me for doing this? It is doing heap allocation, technically. It's a vector. Vectors are allocated off the heap. So I'm returning a vector now, right? So why can I not store a vector into an integer pointer? What's wrong with that? Does that even make sense? Can you put a vector into an int pointer? Int pointers only point to ints. They don't point to anything else. So what do I need to change here? The integer pointer can only hold a single value, not a whole array. There is no difference. So an integer pointer can either point to a single integer, or it can point to an entire array. Because when you point to an entire array, you're pointing to a single integer. You are pointing to the first one. So this is a major, massive weakness in the type system of C++. There is no way to indicate if you are pointing at a single element or if you're pointing at a whole range of elements. And it's really bad because, for example, the deleter needs to, it'll only work with the right thing. If it's pointing to an array, it needs to call the delete with square brackets on it. And if it's pointing to a single integer, you have to call delete with no brackets on it. And there's nothing in the type to indicate which one you're supposed to be calling. So it's something that actually really irritates me about the C++ type system is A pointer says, yeah, here's the beginning of a range of memory. Where's the end? I don't know. Right? When you call make array, it doesn't tell you what was one integer made, was 100 integers made. There's no way of telling unless you go into the function itself and look at it. Okay? So there's a reason why I don't like this style of coding. So yeah. So what needs to happen here is this needs also to change to a vector of integers named R2. And now that line compiles. Cool. Do we got stuff still broken? Yep, absolutely. So we have to come down here. We can see here we're accessing row 1, column 6. So I'm going to refactor this, YYP, comment it out so I don't forget what I was doing. And I'm just going to do a little bit of that. And now I have refactored it so that it is accessing row 1, column 6. This one's accessing row 4, column 2, YYP. And now it's accessing row 4, column 2. You see how that works? When you refactor, you start at the source and you kind of weave your way through. There's a thread where that vector of vectors that used to be an array. You follow that as it traces through the code, and it's going to fail compilation over and over again. You just sort of follow it along until you get to the end. And we're almost at the end. So here we got print array. So print array doesn't like taking a vector. So that we could refactor. As it turns out, we actually already have print vector. So, you know, what I would normally do is refactor this, right? But I don't need to because I've actually already made it. So I'm just going to cheat a little bit here. Normally you wouldn't be able to do this because you'd actually have to write it, you know, yourself. But it's already done, so I'm not going to rewrite it. And then finally, we have come to the end of the line, the end of the thread. What does it take to delete a vector? A vector does heap allocation, right? Do we need to delete a vector, or does a vector delete itself when it comes to the end? Does it free up its own memory? What do I need to do here? It's not compiling. What do I need to do to make sure the vector frees up its memory? This vector is responsible for 100 innocent integers. What do I need to do to make sure that this thing deletes itself? Delete the delete. Very good. Done. Just don't do anything. when array2, when the vector here named array2, when the vector of vectors goes out of scope, it frees itself up. Done. You can't, like, it's just so nice. You don't have to worry about news. You don't have to worry about deletes. The size comes with it. It's really nice. And so that was a successful refactoring from a 1D array into a 2D vector. And you can see, like, it takes work. But at the end of the day, you can now gain all the benefits of a vector. You can do things like have range-based for loops, right? We were able to use range-based for loops, whereas here we couldn't. You can't do a range-based for loop on a pointer because it doesn't know where the other end of the range is. You can't do a range-based for loop when you have a start and not an end. That's not a range. That's half a range, right? It's like having a beginning and no end, right? So the only thing that range-based for loops can run on are things that have both a beginning and an end. And this is just the beginning. So you cannot do a range-based for loop with this. Okay. How do you turn on the setting that tells you have something that is wrong with your code? That is something that I don't teach my students. The reason for that is because what's happening when I'm doing that? Let's say I screw up something here and I change it to, like, I don't know, less than instead of double less than. It's actually compiling the code constantly over and over again. And so one semester I turned it on for all students, and the server slowed to a crawl. Just with people having Vim open, it was compiling. With one person, it's fine. With 2 people, it's fine. With 40 people, with it compiling every second, the server went. So I don't enable it for students. That said, if you are smart enough to figure out how to get it to work, and it's not easy to get it to work, you're more than welcome to use it. So allow me to say that is a challenge for you. Okay, I'm not banning you from doing it, mind you. it's hard enough to do that if I just leave it like that, only 2 or 3 maybe of the smartest or most diligent students will figure out how to turn it on. And that's enough the server can handle. Okay. So yeah, I am that's all I will say on that. It's fine if you can figure out how to do it, go for it. Otherwise, just compile your code, right? And so if you don't get this error message here, then you have to compile the code, and it will tell you error. You get a giant error here. You scroll up to the top, and you can see that that is the actual problem, and that is on line whatever. That's the problem. Okay. So much easier if you have commander of completion on, which is what we're talking about here. So if you want to figure out how to get it to work, by all means, do it. It's a skill challenge. Yeah, it's an optional side quest. Let's put it that way. It does make development go a lot faster because it'll just instantly tell you when you've done something wrong. That said, it's got no chill, right? Like, so if you're like typing something, you're like, like you're halfway through the middle of this. It's like, okay, I know. It's like, I know. Stop. Like, it just constantly like just nags at you. Like, you haven't finished it. Okay, you're fine. And that's something that kind of irks me about it, because a lot of the times, like, I know what I'm doing. You don't need to tell me I haven't finished the line yet. I know I haven't finished the line yet. I'm still working on it, man. So, all right, what's going on, Bencourt? So that is basically class for today. You guys have the rest of class to work on this homework assignment, Bridges Mountains. Bridges Mountains 40. And you'll see inside of here, that is the equation. That is the spiffy, cool equation. They just unhighlighted for me right there. And so work in groups, go into voice chat with your partners, and start getting cracking on it. Only one report needs to be submitted per group. I'm not collecting these on the server, just like the last one. I want to report on Canvas. And the Canvas, make sure you read the Canvas assignment, because it tells you exactly what you need to do in order to get 100% on the assignment. Like, some people didn't read the data science thing, and they did like 3 data points. And so it's like, well, that's a 3 out of 9, So read the assignments carefully. That's what you get graded on. And basically, yeah, you guys got the rest of class. You got an hour to work in lab time, and Crowley and I are here. Bencourt gave a talk on something completely different yesterday, but he's here to help. He's done both the CSI 40 and the CSI 26 version of it, because guess what? You guys get to do this one again. The CSI 26 people, in fact, their assignment starts where this one ends. So what you finish with here, you will actually use in 2 semesters from now in your CSI 26 class. So it continues. You might hear some of the experienced people like saying they have like PTSD flashback from this assignment. Like Bencourt likes to be like, oh, it's so hard, but it's really not. It's not easy, but it's like not like the end of the world. It's really not. So the amount of work on this is like fairly manageable, especially for a group project. So get cracking. I'm going to stop talking now, and I will be around to help during lab time, as will Crowley and Bencourt. Okay, thanks everyone. Peace.